All right, so keep in mind that you want to follow at Think Fiveable on Twitter, Instagram, and YouTube to stay up to date on all the latest excitement that Fiveable has to offer. Okay, in tonight's stream, we are going to look at finding critical numbers. That's going to lead us to determining when f of x is positive and negative, which we're then going to link to determining when f of x is increasing and decreasing. And then the last piece we're going to look at tonight is determining local maximum and minimum values for f of x. All right, so to start out with, let's talk about critical numbers. Okay. By definition, a critical number of a function f is a number c in the domain of f such that either 1, f prime of c equals 0, or f prime of c does not exist. So we've got two different criteria here that qualify as a critical number. Either the derivative at that value is equal to 0, or the derivative is does not exist. Okay. Now, a couple things to make note of as we start to talk about critical numbers. Okay. A critical number itself is that number c, which is the x value. Okay. But you might also hear other things like critical value or critical point. Okay. While the critical number is your x, a critical value would be the y value that's associated with that. And then, of course, the critical point is going to be your x and your y. Now, keep in mind, if you want to find a y value, you simply plug the x back into the original function. So just be aware of those little nuances in terms of what it's asking for you for, and just pay attention to the verbiage in the problems. Okay. So again, just to recap here real quick, two criteria for critical numbers: f prime of c equals 0, or f prime of c does not exist. All right, so let's put this into action. We want to find the critical numbers of f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. Now, keep in mind, by definition, what we just talked about, we are looking for when f prime of x equals 0, or when f prime of x does not exist. Okay. So first thing we have to do is find that derivative. Okay, take a minute on your own and see if you can come up with the derivative of f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. Not a tricky one, it's a polynomial, so basically just one steps in each term. Once you think you have it, go ahead and comment in the chat what you think the derivative of f of x is. Awesome. Yeah, great. Okay. So, yeah, awesome, awesome, awesome. All right, so f prime of x, as you guys just told me, is equal to 12x cubed minus 12x squared minus 24x. Okay. Now, again, we're looking for two things here. We're looking for when f prime of x equals 0, and we're looking for when f prime of x does not exist. Let's talk about that f prime of x does not exist first. Keep in mind that this derivative we just found is a polynomial, okay? So polynomials are continuous functions, and we're going to find that this derivative always exists. So in this particular case, we're going to find out that f prime of x doesn't ever not exist, okay? But what we do have to make sure that we figure out is when that derivative equals 0. So let's set 12x cubed minus 12x squared minus 24 equal to 0. Minus 24, I just made a mistake. Let's get that x back in there I just left out. 24x equals 0. All right, let's solve this. First thing we want to look for is a greatest common factor. What would my greatest common factor be of this derivative? Perfect, Madeline. We've got 12x that we're going to factor out front, and we're going to be left with x squared minus x minus 2 equals 0. We can take this one step further, and we're going to have 12x times the quantity x minus 2 times the quantity x plus 1 equals 0. Now, keep in mind, based on that zero product property, we can take each factor now and set it equal to 0. So we've got 12x equals 0, x minus 2 equals 0, and x plus 1 equals 0. If I solve each of those, I'm going to get x equals 0, x equals 2, and x equals negative 1. So we just came up with 3 different critical numbers. Okay. This particular question asked me for critical numbers, so I found them and I'm done. If they had asked me for critical values, I would need to plug back those x values back into the original function to get my y value associated with them. Or same thing, if I were asked for critical points, I'd need to find that y value and write them as pairs. Okay. Any questions so far in that first example? No? All right, so let's get some more information out of this. We just found critical numbers 0, 2, and negative 1, okay? If I put those in order from least to greatest, kind of thinking on a number line, I'm looking at negative 1, 0, and 2, okay? So taking those same critical numbers that I just found, I want us to use them to help us determine when f prime of x is positive and when it's negative. Okay, so what I've done is I have made a little chart for us to organize our information. And we're going to look at the intervals from negative infinity to negative 1 to 0, 0 to 2, and then from 2 to infinity. I don't know if you guys can see on your end or not. My view's showing my picture over that number 2 in that bottom interval, but that last interval should be 2 to infinity. And I'm getting these intervals based on where my critical numbers were that I just found in the previous example. So in order for us to figure out when f prime of x is positive and negative, we need to test a number in each of those intervals. Okay, so I don't know, let's pick negative 2. Negative 2 falls in the interval between negative infinity and negative 1. You can pick any number you want in that interval, but you don't need to make it more difficult on yourself than it needs to be. So let's take the test number of negative 2. Okay, and now what we want to do is we want to determine the sign of f prime of x in that interval by plugging in that test number. Okay, so we're going to have 12 times negative 2 times negative 2 minus 2 times negative 2 plus 1. Now, let me go back and clarify for you in case you don't have this right in front of you from the previous example. We found that f prime of x, once we factored it, was equal to 12x times x minus 2 times the quantity x plus 1. So I'm going ahead and just plugging into that factored form. Okay. Keep in mind, too, that this chart asks me for the sign of f prime of x. I don't necessarily care about the exact value that I get when I plug in negative 2 to the derivative, but I care about its sign because I'm trying to figure out if it's positive or if it's negative. Okay, so we can definitely use our sign rules to our advantage here. Okay, 12 is positive, negative 2 is negative. Negative 2 minus 2 would give me another negative factor, and negative 2 plus 1 would give me another negative factor. Now keep in mind these are all connected by multiplication. So what would a positive times a negative times a negative times a negative give me overall? It would give me a negative. Okay, so that tells me that my conclusion is that f prime of x in this interval, negative infinity to negative 1, is negative. Okay. Notation-wise, we could also write this as f prime of x is less than 0. That means the same thing. Less than 0 means that it's negative. Okay. Somebody give me a number between negative 1 and 0 that we could test in the next interval. Sure, negative 1/2 sounds great. It's exactly the number I was thinking of. Okay, so again, I'm looking for the sign now of f prime of x when I plug in negative 1/2. So we're going to have 12 times negative 1/2 times negative 1/2 minus 2 times negative 1/2 plus 1. All right, this gives me a positive times a negative times a negative times a positive. What would a positive times a negative times a negative times a positive give me overall in terms of my sign? Positive, great. Absolutely, good job. Rock on. Good, good, good. All right, so my conclusion then is that f prime of x is positive on this interval, which I also could write as f prime of x is greater than 0. Okay. Take a couple minutes on your own and see if you can come up with whether or not f prime of x is positive or negative in the interval 0, 2, and then also in that interval 2 to infinity. So take a couple minutes on your own and see if you can basically complete this chart, and I'll come back in just a couple minutes and check in with you guys to make sure we agree on those intervals. If anybody gets stuck or has questions as you're filling in the rest of this chart, just ask me in that comment section. All right, I'm going to fill in on my end what I've come up with, and then let's see if you guys agree. I picked the test number 1 in the interval from 0 to 2. I found out that the sign of f prime of x at that test number 1 was negative overall. So that meant f prime of x was negative. Okay. And then in the interval 2 to infinity, I picked the test number 3. I found out that the sign of f prime of x at 3 was positive. So my, oopsie daisy, there we go, sorry. So I found out the conclusion that f prime of x was positive, which I could write as f prime of x is greater than 0. Okay. Give me a thumbs up or a smiley face if the rest of that chart looks good to you, or if you have any questions, feel free to type those in too about anything that I came up with. Good, good, good. Awesome. So if we're clear on the chart, what would be the intervals that f prime of x is greater than 0 on, and what would be the intervals where f prime of x is less than 0? Let's see if I can squeeze this in at the top here. If I want to determine where f prime of x is negative, I'm looking at the interval from negative infinity to negative 1, union from 0 to 2. Let's do the same thing for f prime of x is positive or greater than 0. We've got two intervals we're looking at for here. We've got negative 1 to 0, and then union 2 to infinity. Squeeze it in there. All right, so let's take this information we just determined from our chart, and I want to see if you guys can take this one step further, okay? If f prime of x is positive, what piece of information can you tell me about f of x? What do you think? If f prime of x is positive, what can you tell me about f of x? Yeah, awesome, Sierra. That tells me that f of x is increasing. And similarly, if f prime of x is negative, then we can say that f of x is decreasing. Okay, so to kind of think about where we're at in our stream right now, we found critical numbers. And remember that critical numbers came from where f prime of x equaled 0 or where it didn't exist. We then found out where f prime of x was positive and negative, but that really is also telling me where f of x is increasing and where f of x is decreasing. Okay, so this leads me to the increasing decreasing test. They weren't real creative in the name. It tells me that if f prime of x is greater than 0, so if my derivative is positive on any particular interval, okay, then f is increasing on that same interval. If, you know what, I need to flip a sign here. And it tells me that if f prime of x is less than 0, pardon that typo, the derivative is negative, then f is decreasing. Okay. Super, super careful, and this will be really important on the AP test itself. Be very careful of your language and your notation. We say that f prime of x is positive, and we say that f prime of x is negative. That means the same as f of x is increasing or f of x is decreasing, okay? So you want to make sure that you have those matched up, and you also want to avoid using pronouns. If you say it is increasing, well, what's increasing? The derivative is increasing, the function's increasing. You've got to be very clear and very specific on the AP test itself. So make sure you're avoiding those pronouns and you're being very specific and clear in your language when you need to write something out, okay? Any questions about that increasing, decreasing test? I will take that as a no, but if you have any questions, just chime in. Okay, using the same critical numbers we previously found and we've been using, I now want us to determine when f of x is increasing and decreasing. Now, in the previous example, we used a chart, which is one way to organize your information. I personally am a big number line fan, okay? When I use a number line, I draw my number line and I always make sure that I label it. Remember that this is a number line for f prime of x. That's going to become more important later when you start having number lines for the first derivative and the second derivative and maybe even the original function. You don't want to get them mixed up. So always label, 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 okay? Now, on my derivative number line, my number line for f prime of x, I'm going to put my critical numbers. I'm going to put -1, I'm going to put 0, and I'm going to put 2. Now, I found each of those critical numbers from when my derivative equaled 0. So I'm putting a little z underneath there. Again, just being extra thorough, thinking ahead to what's coming down the road in calculus. And I want to make sure that I know why that number is on my number line, so I'm putting a z under it for 0. Okay, we need to test numbers in each interval. Now, we've essentially already done this in our chart format, so I won't go into it in painstaking detail. But when we test a number, for example, in this interval from -infinity to -1, okay, we found, I think, what did we use before? We used -2. We found out that my derivative was negative in this interval, okay? When I plugged in -1/2, which was in the interval between -1 and 0, I found out that my derivative was positive. In my next interval, I plugged in 1, and I found out that f prime of x was negative. And then in the interval from 2 to infinity, I plugged in 3, and I found out that my derivative was positive. Okay, so when my derivative is positive, it means that f of x is increasing. So really this comes down to language, but it's the same information we already found. I am looking for where f prime of x is positive because that means the same as when f of x is increasing. So f of x is increasing from -1 to 0, union 2 to infinity. And now I want to figure out where f of x is decreasing. So I am looking for where f prime of x is negative. And that happens from -infinity to -1, union 0 to 2. Bada bing, bada boom. So it's all about that language. Okay. Any questions for me about how we design that number line? The importance of the language there when f of x is increasing, f prime of x is positive, f of x is decreasing, f prime of x is negative. No? Okay. So for those of you that like the number line, like myself, okay, I just wanted to go ahead and mention on the side here what I do when I make my number line. The first thing I always include on my number line is any endpoints, if there are any. Sometimes you will have a restricted domain or an interval that you're looking at. You won't all the time, but if there are endpoints, go ahead and put the endpoints on your number line, and then you have to make sure you put those critical numbers. And remember, when we're looking at critical numbers, we're looking where f prime of x is equal to 0 and where f prime of x doesn't exist. And then just to make sure that I've got my information straight on my number line, I label it, okay? I make sure that I put EP under any number that's an endpoint, Z for any number that's a 0, and DNE under anywhere where I found that the derivative did not exist. And then the last thing I do in that number line is I determine where the derivative is positive and negative by plugging in x values in each interval that I've got on my number line. Okay, so that's just a step-by-step outline for you guys, for those of you that like the number line approach. Keeps you organized. All right, so let's try a different function. We've been focusing on that same function the whole time. This time I want us to look at f of x equals x cubed minus 18x squared plus 81. And I want us to figure out where the function is increasing and decreasing. So very first thing we've got to do is find that derivative. So we've got that f prime of x equals 3x squared minus 36x plus 0. So just 3x squared minus 36x. What do I need to do now with my derivative in order to find my critical numbers? So what do I need to do with my derivative now to find my critical numbers? Perfect. Set it equal to 0. So I am setting 3x squared minus 36x equal to 0. Is there anywhere that f prime of x does not exist? You got it. It exists everywhere. It's a polynomial. All right, let's factor this. Take out that GCF of 3x. We're going to be left with an x minus 12. And now let's set each factor equal to 0. So we get 3x equals 0. X minus 12 equals 0. And I come up with critical numbers of 0 and 12. All right, now this particular problem doesn't say make a table, make a chart, but those are good ways to keep yourself organized, or make a number line, okay? I'm all about making that number line. So because I'm looking for where my function is increasing and decreasing, I know, oh, that means I need to figure out where f prime of x is positive and where f prime of x is negative. Let's make a number line and see what happens. So I'm going to label this number line as f prime of x. And I am putting on my number line 0, which came from my derivative equaling 0. So I put a z under it. And I am putting 12 with a z under it as well. No endpoints, no DNE. We're good to go. Okay. So now I need to test a number in each interval. Okay. Negative infinity to 0. Let's go with -1. Keep it simple. Now again, keep in mind that I only need to figure out the sign of f prime of x. I don't need to figure out what f prime of -1 actually is. I just need its sign. Okay, so use those sign rules to your advantage. And I like to use the factored form because it's going to be easiest to see positive times a negative or whatever your signs are that are being multiplied. So we're going to have 3 times -1 times -1 minus 12. So I'm going to have a positive times a negative, which overall will give me a positive. What do you want to plug in between 0 and 12? Give me a number between 0 and 12. 5, my favorite number. All right, so we've got 3 times 5 minus 12. So positive times a positive times a negative. So overall, we're looking at f prime of x being negative from 0 to 12. All right, and then we've got to pick another number in that last interval, something between 12 and infinity. What do you want to plug in there? $100, sure. I picked 30. Whoops. Leaned on my screen. There we go. All right, we went with 100. I picked 13 on my own paper when I did it. So we're going to have 3 times 100 times 100 minus 12, which is going to give me positives across the board, which gives me an overall positive. So f prime of x is positive in the interval from 12 to infinity. All right, so we need to answer the question. Write in the comments for me, where is my function increasing and where is my function decreasing? So in the comments, go ahead and write for me where the function is increasing and where the function is decreasing. All right, so we've got negative infinity to 0 and 12 to infinity for increasing. Awesome. Can somebody else give me the decreasing? Great, 0 to 12. So again, being real careful about my language here when I write my final answer, because this is the function that's increasing and decreasing. I'm going to say that f of x is increasing from negative infinity to 0, union 12 to infinity. And I'm going to say that f of x is decreasing from 0 to 12. Nice work. So thinking about that same function, what's the graph of f of x equals x cubed minus 18x squared plus 81 look like? This might be hard to answer in the chat feature, but can anybody describe what that graph looks like? No? Okay. It might be hard to do in words. like a parabola changing based on the x and y intercept. So because this is degree 3, so parabolas are usually associated with degree 2 quadratic equations. This one's degree 3, which is cubic. But again, this is hard to put in words on a chat feature. So let's I'll draw out for us what we, and this is just very generic, okay? Our cubic function, I kind of think of it as snake shape, okay? What other information, based on what the shape of this graph would look like, the intervals that we just found that the function was increasing and decreasing on, what other information do you think I could get at this point from my critical numbers, my intervals of increasing, decreasing, the knowledge of the shape of this graph? Any other thoughts what other information I could get at this point? So I could potentially find x and y intercepts. I don't disagree with that. It's not quite where I was going in my mind. If I look at my intervals where this is increasing, and then I look at my interval where this is decreasing, what do you notice at the points where my graph changes from increasing to decreasing or decreasing to increasing? Okay, I totally agree with you, Sierra. The slope is 0, and so that means that's happening at my critical numbers. What else? Does anybody have any other thoughts about what those particular points are in relationship to this graph? Okay, I don't disagree. Just so we're not really going into inflection points tonight because that's dealing with the second derivative. But remember, inflection points are where that concavity would change, okay? This point right here is a relative max. And this point right here is a relative min. So the connection that I was trying to kind of draw out of you guys was the relationship between critical numbers, f of x increasing, decreasing, my first derivative being positive or my first derivative being negative, in relationship to where I might find a relative maximum and a relative minimum, okay? So here's what the first derivative tells me. The first derivative tells me that if I have a critical number c, yes, exactly. So when the signs change on the chart or my number line for my derivative, I'm going to find out that I have a max or a min, exactly. So if I have a critical number c and my function's continuous, if f prime changes from positive to negative, then I end up with a local maximum, okay? If f prime, my derivative, changes from negative to positive at my critical number, then I know that f has a local minimum. And every once in a while, you're going to find that f prime stays positive or f prime stays negative to the left and right of a critical number. And in that case, it doesn't have a max or a min at that critical number, okay? But big take-home points here is that if f prime changes from positive to negative, we have a local maximum. F has a local maximum, my original function. And if my derivative changes from negative to positive, then my original function has a local minimum. Okay, so let's put this into action. Let's see what this looks like. Okay, I want us to find the local extrema of y equals x to the fourth minus 4x cubed. Now, local extrema is just that combined fancy version of I want us to find the local maximum and the local minimum. Although it directly says to find the local max and min, in your mind, you want to be thinking, okay, that means I need to find the critical numbers. I need to make myself a number line. I need to find out where my derivative is positive and negative. And then from that information, I'm going to be able to find out my local extrema. All right, so let's go to town. All right, we've got y prime equals 4x cubed minus 12x squared. So I'm taking that derivative, and I need to do that because I need to find my critical numbers. Critical numbers happen where my derivative equals 0 and where it does not exist. So far, we've been dealing with polynomials, so we haven't had to worry about where the derivative does not exist. And we are going to factor out a 4x squared to be left with x minus 3 equals 0. This is going to give me two critical numbers. I'm going to have the critical number x equals 0, and I'm going to have the critical number x equals 3. I am going to make myself a number line for f prime of x. And I'm going to put on my number line my critical numbers 0 and 3. And I'm going to label them with a z for 0. All right, let's test some numbers. What number do you want to plug in the interval from negative infinity to 0? Sounds good, -2. Now again, keep in mind, I only care about the signs in these intervals. So if I use that factored form, I'm going to have 4 times -2 squared times -2 minus 3. Keep in mind that when I square -2, anything squared is going to result in a positive. So I'm going to have a positive times a negative. Overall, I have a negative there. So f prime of x is negative from negative infinity to 0. All right, let's plug in 1 for that interval between 0 to 3. So we're going to have 4 times 1 squared times 1 minus 3. Positive times a negative. From 0 to 3, I find that my interval is still negative. F prime of x is negative from 0 to 3. And what do you want to plug in greater than 3? In that interval from 3 to infinity. 4. Sounds great. So we're going to have 4 times 4 squared times 4 minus 3, giving me positives across the board. So 3 to infinity, f prime of x is positive on that interval. Okay, so let's talk about what we know now. We know that f prime of x is negative from negative infinity to 0, union 0 to 3. We know that f prime of x is positive from 3 to infinity. And that tells me that f of x is decreasing from negative infinity to 0, and 0 to 3. and that f of x is increasing from 3 to infinity. Now, this question doesn't specifically ask me about when my derivative is positive and negative or when my function is increasing and decreasing, but I need to know that information to determine where it has a relative maximum and where it has a relative minimum, okay? So where would I have a relative minimum for this particular function? Sounds good. So f of x has a relative minimum at x equals 3. Where does f of x have a relative minimum or relative maximum? Nowhere. Good. There is no place on that number line where f prime of x changes from positive to negative. So f of x does not have a relative max. Now, we haven't quite answered this question, actually, okay? When we are asked to find the local extrema, when we're asked for max and min, we actually need to give a y value. So I know that f of x has a relative minimum at x equals 3, but I haven't actually said what the relative minimum is. How would I figure out what the relative minimum is? Exactly. I need to plug my x value back into my original equation. So I'm going to take 3 and plug it back into my original equation. I'm going to get 3 to the 4th minus 4 times 3 cubed. And when I do that, I should find that this equals negative 27. So the answer to this question would actually be that f of x has a relative minimum of negative 27. Any questions on this particular example? No? Okay, let's try another one. All right, we are finally getting away from polynomials. Okay, this time I want us to find the local extrema for y equals x squared over x minus 2. Now, very first thing I have to do is find that derivative, set it equal to 0. I also, in this case, have to figure out when my derivative does not exist. So first thing we're going to do, though, is actually find what that derivative is. What rule are you guys going to use to take the derivative of y equals x squared over x minus 2? Quotient rule, excellent. All right, so when I set up my quotient rule, and you may have seen this if you've seen some other streams, I set this up in a little grid for myself. Again, just a way to keep myself organized. I put the numerator in the upper left, the denominator in the upper right, and then I take the derivative of each piece. So the derivative of x squared would give me 2x. Derivative of x minus 2 would give me 1. And I'm going to criss and cross here, and because it's the quotient rule, I know I have to subtract the two pieces. So starting in the bottom left, I'm going to have that y prime equals 2x times x minus 2 minus x squared times 1, which is just going to be x squared. And now this is the part you got to remember, all over the original denominator squared. All right, we've got a derivative. Let's clean it up a little bit, though, because we're actually going to have to use this. So this would equal what? 2x squared minus 4x minus x squared all over the quantity x minus 2 squared. And 2x squared minus x squared would give me an x squared, and I still have minus 4x over x minus 2 squared. And we could actually go one step further here and factor an x out in the numerator to be left with x minus 4. Okay. Two things we have to do. We need to set the derivative equal to 0, and we need to set or find out when the derivative does not exist. Okay. Keep in mind that if I have a rational function, a fraction, and I'm going to set it equal to 0, what is it that I really care about equaling 0? So when I have a fraction equal to 0, we really only care about when the what equals 0. Numerator, exactly. So I'm going to solve this as x times x minus 4 equals 0, which is going to give me 0 and 4. So this came from f prime of x equaling 0. But I also have to find out when f prime of x does not exist. Where is my derivative not going to exist in this case? Great, when x equals 2. And we get that by setting the denominator equal to 0. So when I go to make my number line this time for my derivative, I'm going to have on it 0 and 4 as zeros. And I'm also going to have 2 on there, but I'm going to label that with a D and E. That way I'm very clear about what's on my number line and why it's on my number line. Take a minute on your own and see what happens. What signs do you come up with for f prime of x if you plug a number in the first interval from negative infinity to 0, a number in that second interval from 0 to 2, a number in that third interval from 2 to 4, and then a number into that last interval from 4 to infinity. So on your own paper, take a couple of minutes to see if you can come up with the signs for each of those intervals. Once you think you've got the signs for those intervals, go ahead and put in the comments what signs you came up with from left to right. Positive, negative, negative, positive. Sounds good to me. Give me a thumbs up in that comments if you agree. Great, Cammie. Everybody else on board too? Okay, so we've got to answer our question now, okay? We know that f prime of x is positive from negative infinity to 0 and 4 to infinity. We know that f prime of x is negative from 0 to 2 and 2 to 4. And all that translates to the fact that f of x is positive from negative infinity to 0, 4 to infinity. And that f of x is decreasing from 0 to 2 and 2 to 4. We want to find the local extrema, though. We want to find the local max and the local min. For my local max, I'm looking for where f of x is changing from increasing to decreasing. At what x value is f of x changing from increasing to decreasing? Good. So we know that we're going to have a local, or f of x is going to have a local max at x equals 0. But again, we haven't actually answered the question, because in order for us to say what the local maximum is, we need to plug 0 back into my original function and actually get out that y value. So let's go ahead and do that. If I plug 0 back into my original function, I'm going to get 0 squared over 0 minus 2, which is going to give me 0. So f of x has a local maximum of 0. All right, now we need to look for where f of x changes from decreasing to increasing. What x value is that going to happen at? Good. So f of x is going to have a local minimum at x equals 4. We got to plug that 4 in. We're going to have 4 squared over 4 minus 2, which is going to give me 16 over 2, which is 8. So f of x has a local min at, not at, rewind for me. Whoa, what just happened? There we go. A local min of 8. Okay. Questions from anybody? Was there a local max or min at an x value of 2? Nope, because the derivative didn't exist there, right? We can't have a local maximum where the derivative doesn't exist. But sometimes I find that students still try to use that critical number as well, but just doesn't happen. The other thing to keep in mind, and we've seen some good examples of this tonight, but a lot of students fall into the trap of just kind of assuming that their signs are always going to alternate. But this example is a good one where it doesn't, where it's positive, negative, negative, positive. Sometimes students just automatically think, oh, it's positive, negative, positive, negative. So just make sure you don't fall into that trap either, okay? Let's do one more example together. I know we've been an hour, but I want to do one more with you, okay? This next one, I want us to find the local extrema for 4x squared times 1 minus x squared. We've got to find the derivative. What rule are you going to use to find this derivative? Okay, Cammie, I don't disagree with you that we could use product rule. Was anybody thinking anything different? Yeah. So, Cammie, I don't disagree with you at all that we can use product rule. We've got 4x squared times that quantity, 1 minus x squared. But keep in mind, with the AP test, we're going to want to make sure that we are efficient with our time. And if we can do 1 steps and use that power rule with 1 steps, it's going to be even faster for us than using the product rule. And sometimes we have situations like that with the quotient rule too. So right off the bat, we can just do some quick distribution and say, okay, that means f of x is the same as 4x squared minus 4x to the 4th. And now this is way easier to take the derivative of. We would get that f prime of x equals 8x minus 16x cubed. Okay. Now you're going to get the same result if you use the product rule, but that was quick. Just some distribution, and then we can use the power rule with some 1 steps. Okay. Let's figure out where this derivative is equal to 0. So we've got 8x minus 16x cubed equals 0. All right, let's factor out an 8x, and we're left with 1 minus 2x squared equals 0. Let's be real detailed in our work here. We're going to set 8x equal to 0, and we're going to set 1 minus 2x squared equal to 0. In that first equation, 8x equals 0, if we divide both sides by 8, we would get 0. So we've got our first critical number. Next, we want to figure out 1 minus 2x squared equals 0. Any thoughts on how I should solve this one? Okay, we can subtract the 1. We get negative 2x squared equals negative 1. What would I do next? Divide by the negative 2. I get x squared equals 1/2. Now what's next? What do I have to remember when I take the square root? This is a common place that my students make a mistake. Yeah, you've got to make sure that you write plus or minus the square root of 1/2. Okay, and we could simplify that into plus or minus the square root of 1 over the square root of 2, which would give me 1 over the square root of 2. Now, I personally am not a teacher that makes you rationalize the denominator. If your teacher wants you to do that, you certainly could in this case. The other thing we could do back here is we actually could factor this, okay? Sometimes people don't realize we can factor it because 2 is not a perfect square. But we know the square root of 2 times the square root of 2 is what gives me 2. So I actually could factor this into 1 plus the square root of 2x times 1 minus the square root of 2 times x equals 0. And if I solve that, I'm going to get positive 1 over the square root of 2 and negative 1 over the square root of 2. Either way is going to work, though. Okay, so sometimes I have students at this point that feel a little bit uncomfortable with the fact that they've got square roots in their answers. Don't let that worry you, okay? We are going to make our number line just like always. And we are going to put on our number line negative 1 over the square root of 2, 0, and positive 1 over the square root of 2. And these each come from my derivative equaling 0. Is there anywhere here where my derivative doesn't exist? Nope. All right, so let's plug in some numbers. What number would you want to plug in that is less than negative 1 over the square root of 2? Sounds good. I like negative 1. That's what I did on my paper. And when you plug negative 1 into the derivative, do you find that f prime of x is positive or that f prime of x is negative? Positive. Good. All right, now, what number should I pick that's between negative 1 over the square root of 2 and 0? Yeah, great. Negative 1/2. That's a perfect number to plug in. And when I plug in negative 1/2, I should find out that f prime of x is negative. Okay. Between 0 and 1 over the square root of 2, we could plug in positive 1/2. And we'll find that our derivative is positive. And greater than 1 over the square root of 2, we might want to plug in 1. And we'll find out that our derivative is negative. Based on our number line that we've just created now, at what x values does f of x have relative maximums? So we're looking for where f of x changes from increasing to decreasing. Excuse me. Awesome. Negative 1 over the square root of 2 and positive 1 over the square root of 2. So guess what? We don't just have one relative maximum. We actually are going to end up with 2. Okay. What's going to happen when I plug in negative 1 over the square root of 2 into my original function? Because remember, I need to get my y value out. what's going to happen when I plug in 1 over the square root of 2 into my original function? So what would be the y value associated with 1 over the square root of 2 and 1 over the square root of 2 on my original function? Okay, so what am I going to end up getting at for a y value? Because that happens, things are actually going to kind of work out nicely for me. My x value looks a little crazy, but my y value is actually going to come out really nicely. Exactly. We're going to get out that it has a relative maximum of 1 at x equals, so you did 1 over the square root of 2. And guess what? Because they're squared, if I take a negative number and square it, I'm actually going to get the same result. So I'm going to find out that f of x also has a relative maximum of 1 at x equals negative 1 over the square root of 2. All right, let's talk minimums. Does this function have a relative minimum? So yeah, exactly. So when x is 0, my function is changing from decreasing to increasing. So I'm going to find that f of x has a relative minimum at x equals 0. When I plug 0 back into my original function, what do I get out? 0. So I'm going to have that relative minimum of 0 at x equals 0. I switched language on you a little bit in this last example. I just kind of noticed this as I was writing it. Local maximin and relative maximin, they're interchangeable. I noticed as I was writing on this slide, I wrote relative. On the previous slide, I wrote local, I believe, but same thing. So just to kind of recap, okay, big takeaways. Critical numbers happen when the derivative is equal to 0 and when the derivative does not exist. When my derivative is positive, it's the same as saying that my function is increasing. When my derivative is negative, it's the same as saying my function is decreasing. When my function changes from increasing to decreasing, I end up having a relative or local maximum. When my function changes from decreasing to increasing, I have a relative or local minimum. But keep in mind that when you answer questions about maximum or minimum, the maximum and minimum values always refer to the y value. So you've got to plug that x in to get out your y value, okay? I had one more example in my notes that I was going to work through with you guys, but I know we're already over on time. Does anybody have any questions about what we discussed tonight? Ooh, good question. Okay. So I did not get into absolute max and min on these examples. I only talked about relative or local max and min. In order to get your absolute maximum and minimum, you have to plug in all the x values that have potential. So let's say you've got like two candidates for, you have two candidates for maximums. You would need to plug both of those in and see which one was the maximum, which one was the highest, and that would be your absolute maximum. Same thing with minimum. If you had a couple candidates for minimum, you would have to plug those x values in, get out your y, and see which y value is the absolute lowest. Now, that being said, though, you also have to keep in mind the end behavior, okay? So let's say I even just had like a cubic graph, okay? I would end up with a relative maximum here and a relative minimum there. But my graph goes all the way up to positive infinity. In that case, you do say that there is no absolute maximum because it's going all the way up to infinity. This one's going all the way down to negative infinity, so you would say it has no absolute minimum. A couple other quick examples might be something like a parabola. This relative minimum would also be your absolute minimum. It's the only candidate, though, but is the lowest that graph goes. Based on its end behavior, they both go up. There would be no relative or absolute maximum in this case. Let's get a little bit fancier. Let's say we have something like this. Okay. We would have two relative maximums. We would have, one relative minimum. But based on these two maximums, I'm looking for which one of those two actually ends up being higher. So I would have to take the one that has the higher y value. Does that help answer your question a little bit? Great. Good, good, good. Awesome. What other questions you guys have? None? Okay. So just wanted to remind you to keep checking Fiveable for upcoming streams for next week. We always want you guys to join us and be in on the excitement. We absolutely love having you guys attend our streams. Check for them on Twitter, Instagram, YouTube, and share with your friends that these live streams are up and running and when they are, and feel free to join and invite your friends to as well. I'll stick around for a couple more minutes if anybody else has other questions. Otherwise, have a wonderful night, and thanks for sticking with me even though we went a little bit over. See you guys later. Bye. You're welcome, Cammie. Thanks for attending. We loved having you. You're welcome. Thank you. And you were a great participant. Thank you. Mm-hmm.